Hey, check it out. Definition of derivative. This one's easy. This is like definition of derivative elementary time. Let's take a look at an example immediately. Here's the type of challenge you'll receive. Find the derivative of the function using the definition, also known as the difference quotient. And we're given the function f of x equals x squared plus 3. All right, so we've got to write down the blueprint for the definition of derivative. That is the limit as h goes to 0 of f at x plus h minus f at x all over h. Now we've got to use that for our function f of x. These are composition functions. So on the top, the way I do this is I take the white f of x. Wherever I see an x, I want to plug in x plus h. Okay? So when we take a look at this, and I've written the whole thing down here, that first f at x plus h, take a look. Instead of x squared, I go x plus h quantity squared. Don't forget the plus 3. Minus f of x. Well, I know what f of x is. That's exactly what's written in white. X squared plus 3. All over h. So there's the first step in doing these problems. You have to compose the function. You've got to take wherever you see an x and plug in an x plus h. That might exist in more than just one location. Take wherever you see an x and plug in an x plus h minus, and then subtracting f of x is easy. You're subtracting the original function f of x. All over h. Don't lose track of that. Also, while I'm at it, the limit as h goes to 0, you've got to rewrite that every line of work. So our goal when we get problems like these, we got to eliminate that h in the denominator. You can see with a direct substitution, if you plug a 0 in for h, you're dividing by 0 and getting an undefined limit. And you will find that these problems all work out so that algebraically you're going to be able to rid yourself of that h on the bottom. It's the h on the bottom in the denominator that is the problem child. Worth noting. You get h's on top when the dust clears. That's all right. We can evaluate the limit. That h that exists on the bottom is the problem child we got to get rid of. Okay? So you can see what I've done here is simply expanded x plus h, 2x squared plus 2xh plus h squared. I still got that plus 3. The exclamation point, the warning there, you got to make sure you're subtracting that whole quantity. So you're going to have a minus x squared minus 3. That minus 3 is not a mistake. I essentially distributed the negative 1 that exists in front of the quantity there. All right? So I've rid myself of the parentheses on top, and I have subtracted that second quantity correctly. Remember, you're still all going to be over h. Now, you're going to see some things on top that eliminate themselves. You see that? You got an x squared and a minus x squared. Well, that's history. See anything else? I agree. You got a plus 3 and a minus 3. That's history. And you might notice here that the remaining two terms that you have both contain at least one h. So your next step is going to be to factor out that h. I still got the limit as h goes to 0. And I factored out the h. H times quantity, 2x plus h, all over h. By factoring out that h, that top to bottom relationship with the multipliers h's, I can now rid myself of those two h's. I've gotten rid of the problem child h on the bottom. Awesome. And I'm now left with the task of evaluating the limit as h goes to 0 of 2x plus h. Remember, as I said earlier, it's the h on the bottom that I've got to get rid of. It's okay if you have an h on the top. You can still do the problem. In fact, evaluating this limit at this point is a simple direct substitution. I put a 0 in for that h and evaluate the limit. I put a 0 in for that h, and the limit as h goes to 0 of 2x is a simple answer, 2x. Done. So that's about as easy as they get for the definition of a derivative let's look at one that's a touch more difficult.